So our next talk is Jennifer B. from UC Irvine, who's also visiting Fields Institute this fall. And her title is chi less than or equal to chi star via classical entropy of microstates.
Thank you so much, Jamie, and thank you to the organizers for having me here. It's really nice to be here. This is a joint work with David Jekyll and is a proof of this kind of known inequality, but for the conditional case of the free entropies. So before I jump into a bunch of hopefully not too technical details, I'll give a really brief overview of what these symbols are saying. So we've got chi, the microstates free entropy, some notion of entropy inspired by Boltzmann's characterization via some counting of microstates, and then the non-microstates free entropy chi star, which is based on some infinitesimal approach related to a quantity called the Fisher information. And this results in its original state as just the microstates free entropy is bounded above by the non-microstates free entropy was originally proved by Capitan and Gionet using some large deviation theory and stochastic PDEs. This was like a sub-result of their paper in 2003. Our proof today generalizes to the conditional case and is also entirely different in the sense that all of the methods are somehow very elementary. And so the main theorem that the next 30 minutes will be about the proof of is just that chi is less than or equal to chi star when I condition on any separable von Neumann subalgebra A. Okay, so before I jump into the free case, I'll just say a few things about classical conditional entropy. In the case of classical random variables x and y, the entropy is just defined as the expectation of negative rho log rho, where rho is that conditional density. And in the talk today, all my random variables will just be random matrices. And you can make some appropriate renormalization of the entropy so that the expected value and the variance of these tuples doesn't depend on the dimension of the underlying matrices, which is what we want because I'm going to take large n limits. All right, so when I move to the free case, for the rest of the talk, I'll fix the following notation. M tau is some tracial von Neumann algebra, A is some separable subalgebra, and I have some possibly infinite tuple of generators for that subalgebra. And for much of the talk, I'll actually be able to fix a tuple of matrix microstates for that underlying generator Y. And the definition, the symbol that we'll be working with a bunch are these microstate spaces, which were already introduced in some part by Dan Wojciechowski this morning. I have a slightly different definition, but I'm just saying for any neighborhood of the law, I can define the following microstate spaces. It's just the n by n matrices that have operator norm bounded by R and then somehow converge to the law of XY. Sorry. Okay, and then we do the usual definition of the microstates free entropy. In this case, I'm starting with Shleitenko's relative microstates free entropy. And the key thing here is I have the exact same formulation that Dan showed this morning, and the quantity I'm taking the log of is the Lebesgue measure of these microstate spaces when I choose approximating microstates yn and generators y to maximize whatever this Lebesgue measure is. And in this case, once R is big enough, bigger than the operator norm of X, this thing is constant. So in some sense, I can restrict down to bounded microstates. Now, what I would really like to do for all of the analysis and the proof is not have to worry about arbitrary microstates for the Ys. I would really like to just fix them. And the way we're going to do that is going to be via embeddings into matrix ultraproducts. I'm not sure how familiar the general audience is with this, so I'll say the following. Fixing a tuple of matricial microstates for my generators Y that converge in non-commutative law, that's what I'm using this squiggly arrow for, is equivalent to fixing an embedding of the subalgebra into a matrix ultrapower. And it's kind of the natural embedding. I take my generator element Yj and I map it to whatever this object, the equivalence class of the matrix microstates in this big ultrapower. So in case you're not familiar with ultrapowers, the idea is I want to make asymptotic properties exact. And the construction goes as follows. This curly U is a non-principal ultrafilter on the natural numbers. This is some concept of what a big set should be. So it's closed under finite intersection, superset, and for any subset of the naturals, either that set is in U or its complement is in U. And non-principal just means that it's not generated by a single element. It's not just like all sets that contain 5 or something. And the key thing about this is that you can do some notion of taking the limit, which is defined down here. I just say that the ultralimit of some sequence xn converges to x. The set of indices where I'm epsilon close is in the ultrafilter. And this limit always exists, and it captures the notions of limit infimum, limit supremum, arbitrary subsequential limits, and so on. So then I can form this matrix ultraproduct by taking bounded sequences of n by n matrices and mod out by those which have traces going to 0 in the ultralimit, and then I complete with respect to an ultralimit of these n by n normalized traces. Okay, and the idea here is once I fix an embedding, I should be able to just fix matrix microstates and then just worry about subsequences in that sense, and all of the analysis gets easier because the conditioning is determined. Yeah, okay, this should be xn star xn, yes, sorry. Okay, so I copy and paste my definition for the microstates free entropy, and now I throw a ultrafilter on there, and instead of considering the supremum of the Lebesgue measure of the microstate spaces over all microstates yn, I fix some yn converging to y. And we prove in the paper, okay, this is independent of the actual choice of these matrix microstates and the actual choice of the generators. It only depends on what the subalgebra is and what the embedding of that subalgebra into the matrix ultraproduct is. Okay, in that case, I can just take the supremum over all embeddings into some matrix ultraproduct, and then the supremum over all ultrafilters, and I recover Shliak-Tenko's relative free entropy. And now I can actually just work with a fixed sequence of microstates. So all analysis gets easier. Okay, so I promised that the proof went through some relationship to classical entropic quantities. And there will be 2 theorems that relate the microstates free entropy with the classical one and the non-microstates free, sorry. So A is separable. Y is a tuple of generators for A. No assumptions on A other than it's a separable subalgebra of M, yeah. This is independent of my choice of Y. So you can do whatever you want to do. Yeah, yeah. Okay. All right, so the first kind of main result is a relationship between this microstates free entropy for some fixed microstates and some fixed ultrafilter is actually just the supremum of an ultralimit of the classical entropy on these microstates. I have some technical assumptions. All right, the law of x and y has to converge in probability to the law of xy. Great. I have some uniform upper bound on the ultralimit of the operator norms of the xn's. And then on the 2 norms, I have a exponential decay in probability outside of some compact set. But this is uniform in n and not in the ultralimit. And I would like to sketch some of the ideas behind the proof of this. And of course, I'm trying to show equality of 2 things. Just trying to show, all right, whatever this is the supremum of these objects. So of course, I'll just do 2 inequalities. So assume I have some matrix microstates xn that satisfy properties 1 through 3. I want to show that this is bounded above by chi to the u. And I just use the following classical fact about entropy. If I take some partition of my measure space, in this case, the m tuples of n by n self-adjoint matrices, then I can bound the partition of some xn's y, the entropy of the xn's andyn's from above by the following quantity that just has to do with whatever the partition sjn is for the space. And I'll fix the following partition. If I fix a neighborhood O of the law of xy, then my first set is just whatever the microstate space is. My second set is, all right, I have some ball of radius c plus 1. What is c? I said earlier that this condition 3 holds, and c is the thing that gives me, I don't know, like the radius of this compact set or something. Okay, so then I take whatever that ball is, I subtract the microstate space, and then it's just a bunch of annuli after that. And what I do is, on each of these annuli, you can use some Stirling's estimate for the volume of the ball, along with this exponential decay in the 2 norm of x, to show that these measures of these annuli go to 0. Can do the same thing for this set using the fact that the laws of the xn, yn's converge in probability to the laws of xy. And here you can basically approximate this arbitrarily well up to a plus epsilon using these sets once n gets large enough, again by convergence in probability. So in broad sketches, that's how the proof goes. I have to do the opposite direction now. And in the opposite direction, I want to actually construct some matrix tuple xn that satisfies that the classical entropies is larger than chi to the u. So in this case, I start with any nested decreasing sequence of laws. So they decrease to the law of xy, and I define the following sets. Okay, they're sets of indices that satisfy that this quantity that appears in the definition of chi to the u is 1 over k close to chi to the u. So chi to the u is actually, I take the ultra limit of this thing, and then I take the infimum over neighborhoods. So this is possible, it's not empty. In fact, by the definition of the ultra limit, each of these sets AK is in my ultra filter U. So these are very large sets of indices. And now I can just choose for every n in AK minus AK plus 1. By construction, these things are nested decreasing. Yeah. So I have some unique choice of k for each n, so that I can just choose xn uniformly from the microstate space. If there's any n's that are not in the union of the AKs, I just don't care about them. They're a small set according to the ultra filter, so the ultra limit just doesn't see them at all, and I can do whatever I want on those values. Okay, and then by construction, this thing is larger than chi to the u, because, I mean, that's how I made the sets, right? And then I have to say, okay, these xn's actually satisfy my technical assumptions, but this is actually pretty easy because I'm picking some uniform distribution in here, so they are actually uniformly bounded in operator norm, which implies they're uniformly bounded in 2 norm. So 2 and 3 are satisfied, and then because I'm choosing them from the microstate spaces, I also get convergence in probability for the laws. Okay. So that's a sketch of the proof of the relationship in the case of microstates. I'm going to depart from this picture entirely and talk briefly about the non-microstate picture, and then I'll conclude with a sketch of the main result. So in the non-microstate picture, I said it has everything to do with this quantity called Fisher information. The same thing I defined before, just expected value of negative rho log rho with the right renormalization for the matrices, can be recovered from the classical Fisher information by some integral formula. And this Fisher information, In, is just the 2 norm of a conjugate variable. And what's a conjugate variable? I'm saying that it satisfies the following integration by parts relationship. If I have some smooth function f in the correct number of variables, then when I take the conjugate variable and take the inner product against f evaluated at x and some tuple of y's, I just get the divergence. So you can also think of this as the value of the adjoint of the derivative operator at the identity. Okay, I'm again going to adapt everything to the free case. I need to define some conjugate variable for my von Neumann algebra tuples. And it looks exactly the same where you just do the translation. So I want to say that C is a conjugate variable for x with respect to the subalgebra A if tau of this conjugate variable evaluated against some polynomial is tau tensor tau of the derivative of that polynomial. And here the polynomial is allowed to have coefficients from anything in A, and you can rewrite this to just be approximated by polynomials in my tuple of generators y and the indeterminates x1 through xn. Okay, then I can make the same definitions. The relative free Fisher information quantity is just the 2 norm squared of this conjugate variable. And because I want to talk about a fixed tuple of generators y and fixed microstates and everything, I'm also just going to write it as b star of x given y. All right, then you just copy and paste the same integral inversion formula with the free Fisher information in place of the classical Fisher information. And of course, when you do this movement, you have to replace the M tuple of Gaussian things by an M tuple of freely independent standard semicirculars. But everything else is the same. So now the proof is going to go through some relationship involving this quantity. And then the main result will follow by doing some analysis on this integral inversion formula and combined with the previous result on the microstates picture. So to talk about relating the free and classical Fisher informations, I basically want to turn this integration by parts thing into something that just involves traces and then apply convergence in non-commutative laws. So I first do a lemma that says, look, this free Fisher information is equivalently just the evaluations traced out, tau tensor tau, of derivatives of polynomials in the x variables. Again, where polynomials can take coefficients from the subalgebra A. And the tools there are, again, fairly elementary. You want to approximate the A's by polynomials in the Y's, and then you're able to utilize this integration by parts formula on each like finite subset of the Y's to get this thing to fall out. Okay, and then I have finally this relationship between the free Fisher information and the classical Fisher informations. If I take any sequence of random matrix tuples so that the law of xn yn converges in probability to the law of xy, and then I have the following assumptions, all of the even moments when I take the trace and then expectation in ultralimit is finite. I said earlier that the quantities are all invariant under choice of generators, under the choice of matrix microstates for the y's. And so this assumption will be easy to satisfy. I can just like choose something that does that, and it doesn't matter for the microstates quantity. And then this assumption is going to be satisfied because the xn's are chosen uniformly in some operator norm ball of radius r. Why do I need these assumptions? I only assume convergence and probability of the laws, and I need to upgrade this to almost sure convergence of all of the moments. So once I assume these things, I can upgrade my convergence and probability to actual convergence, and then when I look at this expression in the matrix algebras, if I have trace n, tensor trace n, and then partial p of some xn's, I actually get almost sure convergence in the ultralimit to this quantity in the von Neumann algebra. Okay, So then I have that relationship. I do a little bit of calculus. It's a couple of pages, but none of the steps are actually complicated at all, and I won't get into it here because it's not enlightening. And I get the main theorem. And the main theorem, you'll notice, does not have any of the technical assumptions that the two sub-theorems had. I just have any M tuple of self-adjoint elements in a von Neumann algebra, any tuple of generators for my separable subalgebra A, and any sequence of microstates yn for y. And then you get the inequality that you want. And I don't have to assume all of that extra technical nonsense for the reasons that I gave before, that in the construction of the inequality in the microstates picture, I'm actually choosing xn's uniformly in some bounded microstate space. Okay, and then by taking supremum over all of the embeddings into matrix ultraproducts and all of the non-principal ultrafilters, I can recover the same result for Schleich-Tenko's relative microstates free entropy. And I'll end there. This is just a recap of the main results.